Well, here's a problem that is pretty well known, and probably almost everybody that takes a calculus class sees this problem. Here's what it is. There's a 15-foot ladder. Now, the numbers may change, but here's the idea. You have a ladder resting against a wall. Now, the bottom of the ladder is initially 6 feet away from the wall, and then what's going to happen is the ladder is going to slide away from the wall. So imagine the bottom of the ladder sliding away from the wall. Now, as the bottom slides away from the wall, we want to find the rate at which the top of the ladder is moving down the wall. So a couple things first of all here. We have a 15-foot ladder is resting against the wall. Okay, now the bottom of the ladder is 6 feet, so there's a constant. Now, if the ladder slides away from the wall, so here's a movement, right? And the movement is going to be a rate. So you see that word rate. So what do you think? You think derivative, all right? So we got a derivative. And this is with respect to, look at the top and the bottom. The bottom is in seconds, so it's with respect to time. So we have a distance relative to time. Now, find the rate, all right? So find the other derivative at which the top of the ladder is moving down the wall. So let's start here by drawing a picture. So I'll do it up here. Here's a wall. Matter of fact, I'll do it like this. There's a wall. Here's the ground. Right, so here's the ground. And we've got a ladder that is resting against the wall like this. All right, there's the top of the ladder and the bottom of the ladder. Now, initially, the bottom is at 6 feet. I am not going to do this. I am not going to put a 6 here, right? I'm not going to put a 6 here because that distance is changing. I only want to put constants in at the very end, so don't be putting that 6 there just yet. What I want to put there is maybe some variable that's going to change. So since it looks like a coordinate system, how about if I let the distance between the bottom of the ladder and the wall be x, and what else is changing here? Another variable quantity is the height. So how about, it seems reasonable that that should be y. Now, I've got a picture here, and the picture should help us access the equation that relates x and y. So let's see if we can get the equation. Now, it sure looks like we have a right triangle here. And in fact, there is a constant I can put in here, something that does not change, and that's the length of the ladder, right? The ladder is 15 feet long, right? So the ladder, we're given that is 15 feet long. So I'm going to put in a 15 here. That does not change. So I think we can produce an equation here, right? By the Pythagorean theorem, we're going to have that x squared plus y squared is equal to 15 squared, right? The sum of the squares of the two sides is equal to the square of the hypotenuse. Let's take it just a little bit further. Let's go ahead and square that 15. So we'll get x squared plus y squared equals 15 times 15 is 225. So now let's differentiate with respect to time. So remember that x and y are both functions of time. So what we're going to have is, all right, differentiate this. So remember it's a power, so it's going to be, bring the 2 down in front, so we're going to have 2x, but then dx dt plus, now the y, that's going to bring the 2 down, 2y dy dt equals, now the derivative of 225, well, that's a constant, so that's 0, right? So this is 0. Now, here's what I'm going to do. I'm going to do a little aside here. That was implicit differentiation. Let's be sure that we know where these things are coming from. Where is that dx dt and dy dt coming from? If you already are comfortable with this, just fast forward. But I'm going to show where this comes from. So from here, let's go up here. Now, x is really a function of time, right? X changes as time changes. The bottom of this ladder is sliding this way, right? What's happening here is the ladder is sliding this way. So that x is going to change. And then as x goes out to the right, the top of the ladder is coming down. So that y is going to change. And they change relative to time. So x and y are really functions of t. So I'm going to write this, just to be very explicit here. X is a function of t squared, plus now y changes as time changes, equals 225. So now let's differentiate. Now look what we have here. This is the power, right? I got x to the second power, y to the second power. So I'm going to use the chain rule, or the power rule if you like. Power rule, remember how we say it. It goes like this. The derivative of the outside times the derivative of the inside. Same thing over here. The derivative of the outside times the derivative of the inside. So let's do this. So the derivative of the outside, bring the 2 down as a multiplier and decrease it by 1. 2 minus 1 is 1. So we are going to have 2, here's the derivative of the outside, x of t just to the first. I'll go ahead and write the 1. There's the derivative of the outside times the derivative of the inside, not squared, derivative of the inside. Now the derivative of the inside, that's just the derivative of x. So I'm going to write dx dt. That's where the derivative, that's where that dx dt comes from. So just say what we have. It's the derivative of the outside, 2 x of t to the first, times the derivative of the inside. Now I don't know what the x is, so I'm going to indicate it, dx dt. Now do the same for the y. So bring the 2 down, so plus, bring the 2 down, there's the derivative of the outside, right, to the first, times the derivative of the inside. Now, it's y, I don't really know what y is, so I'll indicate it, dy dt. Now, over here on the right side, we got 225, and 225, that's a constant, and we know that the derivative of a constant is 0. All right, now what I can write is this. If I replace the x of t's and the y of t with just x and just y, we will have this. I'll get the 2x dx dy plus the 2 y of t, I'll just write as a y, and then dy dt all equals 0. All right, and that takes us right back up to, hopefully that explains where this comes from. So now we have the derivatives, so we've differentiated. Now let's substitute the values that we know. Well, we have the 2, and then we have the x. Now here's what I know about the x, right? That's this x right here. So initially, that x is, where'd it go? 6 feet from the wall, right? So x is 6 feet. So what I'm going to get here is 2 times the 6 feet, 2 times 6 feet, times dx dt. Now what is dx dt? Dx dt, we happen to know that. Right here, the 15-foot ladder is being pushed away from the wall. So that's at the rate of 2 feet per second. All right, so dx dt is positive because it's getting bigger, right? It's going away, so it's positive. So this is going to be 2 feet per second. All right, so 2 feet per second plus 2 times, what's this y? Okay, we're going to have to work a little bit to get this y. But it shouldn't be too bad because here's what we know. Let's do that right down here. I'm going to do it at the bottom left. Here's what I know. We have this triangle, right? This triangle right here. Up here at the top, I got a triangle. And when x is 6 and the hypotenuse is 15, it's going to look like this. This is going to be 6. This is 15. And then I have this. This is y. So I get x squared, 6 squared, plus y squared equals 15 squared. All right, so I get 36 plus y squared equals 225. So y squared is equal to 225 minus 36. So I get y squared is equal to 189. And then if I take the square root of both sides, all right, I get the absolute value of y, right, which is the square root of 189. But now the absolute value of y, let's just say, all right, you know, if we do this, we'll get positive and negative, right? Y is equal to positive, negative 189. But since y is positive, because it's the length of a wall, the length of a ladder up a wall, we'll just take the positive. So we'll say that y is equal to the square root of 189. Now what I'm going to do here is I'm just going to approximate it. So on my calculator, I'm coming out to about 13.7. So I'm going to put that 13.7 right up in here. So this is going to give us, put that 13.7 here. Now this is really 2 times 13.7 feet, right? Times, now dy dt. Dy dt, well, that's what we're trying to find, right? Times dy dt. I want to find out how fast this ladder is sliding down the wall. That's all equal to 0. So let's simplify a bit. Let's make some multiplications. We will get up here 2 times 6 is 12, times 2 is 24. So we will get 24, and then what about units? Feet times feet per second. So this is going to be square feet per second plus, and the 2 times the 13.7 is 27.4. And then we just have feet, right? Feet. We don't know the units of that one yet. Well, that's going to be feet, right? That's going to be feet. But let's hold on to that for a minute. So far we have, this is feet times dy dt. The whole thing's equal to 0. Now we're trying to find dy dt, right? Get this. So this is just an equation here. Why don't we subtract this from both sides? So we will get now this. We will get 27.4 feet times dy dt is equal to negative 24 square feet per second. Now the negative's good, right? The negative is good because we want that y to be decreasing. So the negative is going to give us that decrease. Now what we need to do is get dy dt just by dividing by that 27.4. So let's draw that. So we are going to get now that dy dt is equal to negative 24 square feet per second divided by 27.4 feet. Let's get a new page here. We're getting a little tight on space here. So we are going to get now what? Dy dt is equal to negative 24 square feet for 1 second times, now what is this? Isn't it really this? Isn't it really 27.4 feet over 1? So how do you divide? You invert and multiply, right? Multiply by the reciprocal. So let's invert this. Just flip it over. So you get 1 over 27.4 feet. Now, what happens here? Well, the feet here will cancel with one of these. Let's see what we're left with. We are left with dy dt is equal to negative 24 feet times, right, negative 24 feet times 1. I'm going to write everything here. Times 1 over, what, 1 second times 20. All right, so it's 1 second times 27.4. So here's what I get. I get dy dt is equal to, now, negative divided by positive is going to be negative. So we're going to get negative. Now, when I take 24 and divide it by 27.4 on my calculator, I get this. I'm going to round off here in a minute, but it's going to be negative 0.8759. And then what's left on the top? Feet, and on the bottom, seconds. So I get feet over 1 second. So let's just fix this up a little bit. We will get dy dt is equal to negative, how about if we round it off? 0.88 feet per second. That's what we're looking for. So let's just kind of reiterate what's happening here. We've got a wall here, a floor here, and there's a ladder leaning up against the wall. And we're going to move the ladder this way at what? 2 feet per second. Now, as the bottom of the ladder moves, the top of the ladder is going to go down. And what did we say? It's going to go down at what? It's going to go down at, we have to be careful how we write it. It's going to go down. Now the down is the negative. So it's going to go down at what? 0.88 feet per second. Now I want to answer the question. I want to be careful how I answer it. So I'm going to look back at the question. The question says this: find the rate at which the top of the ladder is moving down the wall, right? I already know it's going down from that minus sign. Now how fast is it going down? So let me go back over here. It's going down, not at negative 0.88. The negative means that it's going down, but it's going down, we're going down at 0.88 feet per second. That, I think, is our answer. So going down, how far, how fast? 0.88 feet per second. So let's write an interpretation so we'd explain to somebody what that 0.88 means. How about this? Our interpretation. When the bottom of the ladder, let's just write it here, when the bottom of the ladder is 6 feet from the wall and moving away from the wall at 2 feet per second, the top of the ladder I wonder what language this is. I can barely read it. The top of the ladder is moving down the wall at 0.88 feet per second. And that's it.